a lute, for example. You can tell it's a lute because it has 3 tuning pegs. Anyway, the frequency, I don't know why people loot each other in video games. Looting. I don't know where that comes from. Anyway, all right, so the frequency at which an object naturally tends to vibrate. That is the natural frequency. Now, at that frequency, there's a minimum energy that's required to produce a standing wave. And if I was going to choose out, like, here I am wanting to choose an animation. That's okay. Internet won't cooperate with me again. Anyway, I think about, like, if I was going to vibrate a string, how many antinodes are there? 1 antinode. 2 nodes. And we can do this later on if you like. We can try and wiggle a string to see how easy it is to get this to happen. It's really easy. This is the easiest standing wave to make. But the natural frequency of a body depends on its dimensions and the ability to transmit waves back and forth. So, of course, in the terms of dimensions, we think about the fact that, like, a lot of us are familiar with guitar strings or piano strings. Do you ever notice when you look inside of a piano, the strings are different lengths? They're not all the same length. Okay, those different lengths are going to cause different lengths of standing waves, and those different lengths of standing waves are going to allow different frequencies to be made really easily. Same with, like, a harp, for example, right? Like, that's a nice stringed instrument where the strings are different lengths. Natural frequency examples could be like dropping a metal rod. If I drop a metal rod, it's going to make a clankety clank sound, and that clankety clank sound is going to be dependent on how long the rod is and whether it's made out of aluminum versus iron, right? So if I had 2 metal rods, one that was iron and one that was aluminum, and they're the same length, they're actually going to vibrate at different frequencies because the vibrations travel at different speeds in aluminum than it does in iron. Fair enough. Ringing a small bell versus a large bell. Again, when I think about a bell, like ding-a-ling-ling, if this is my bell, there's the little clacker inside that clacks back and forth and rings the inside of the bell. If I have a little bell as opposed to a big bell, it turns out that the things that are vibrating are larger on that big bell. So that means that the waves are going to end up being larger if this actual casing is vibrating. Larger waves means, what is it, lower frequencies or higher frequencies? Lower frequencies, assuming that they're both made of the same material. So, like, if it's made out of, I don't know, both glass or something like that. I think I have a couple of ceramic bells in the classroom. Here's another one, rubbing a wine glass. And if you rub a wine glass, again, I got a few wine glasses in the classroom, but if you rub a wine glass, it turns out that you'll actually get different frequencies out of these wine glasses depending on if they're full versus partially empty, because the wavelengths and the frequency are going to be different coming off those 2 different vibrating bodies.
Seeing it to shatter.
Oh yeah, you can actually play a note that's just at the right frequency to cause constructive interference in that wine glass, and you could make it to break as well. That's a whole other thing. Because once you find the natural frequency for something, that natural frequency, that lowest frequency at which it'll resonate, you can just keep on playing that frequency over and over and over again continuously, and you can really stress the material out. You can also have a mass on a spring.
No, the material's stressed out now. It's going to get gray hairs.
I feel like I want to stop there because we're going to come back to talking about resonance and how it can stress physical bodies. I'll pause there for now.